Hey guys, welcome back to Food for Thought Physics. Today we're going to be solving two special kinematic cases for the acceleration, velocity, and position functions. So the first of these cases is going to be constant velocity. And constant velocity is exactly as it sounds. The velocity function here is going to be constant. It does not change over time. It is just some constant number all the way through. So basically what we can do here is we can write, well, for the velocity function we can write v of t equals v, some constant v all the time. So if we want to graph this on this graph of v over t, it's easy to graph. It's just going to be some horizontal line here, and we're going to say that this point right here is v. The v value is some constant v all the way through. Right? It's a horizontal line, doesn't change. At all points in time, the velocity is always going to be v. So now let's look at acceleration. We defined acceleration as the derivative of velocity with respect to time, which is going to be the rate of change of velocity with respect to time, which is also the instantaneous slope at any given point on this velocity function. Well, if we look at this velocity function, we see it's a horizontal line all the way through, as like we said. So we know that a horizontal line has a slope of 0 at all points, which means that this acceleration should be 0 at all points, because the acceleration function is just going to be the slope of the velocity function. So it's going to be 0 at all points. So it's going to be a horizontal line at 0. So what we can do is we can write acceleration a equals 0 for constant velocity, because acceleration is the rate of change of velocity, and this velocity is not changing at all. It's constant, so there's no acceleration. Now let's look at position. Position we defined as the integral of velocity with respect to time. That means that the position is the change caused when we have some velocity. So we can do this by, remember, finding the area under the curve here. So let's say, for instance, that we move at this velocity for some amount of time, all the way until, say, here, all the way until some time, which I'll call t for now. Well, then what's the area under this function, this v function here, this straight line, from this line all the way down to the x-axis? Well, this is easy to find, because this makes a rectangle, and we know that the area of a rectangle is just the base times the height. So we're going to say that the area equals just vt. The altitude is v, and the base length is going to be t, so the area is just vt. So since the area is vt, what we can do is we can write x equals vt. But this isn't actually it. X does not just equal vt, actually. This vt simply represents the change in x. The integral just means it's a change, remember? So this vt is this integral area function here is going to be a change in x. So x in this time t has changed by vt. However, just because it's changed by vt doesn't mean we're at vt right now. The position might have started at some value other than 0. So say if the area here, the change is going to be 5 meters, and we started at 1 meter, then our new position is 6 meters. Or maybe we started at 0 meters, and our new position is 5 meters. So who knows? We don't know what the original position is. It's not given by this area. The area only tells us the change. So what we're going to do here is we're actually going to add another term. So we're going to add x with a small subscript 0 here. So x sub 0, this is also read as x naught, which I'll write here. Not spelled N-A-U-G-H-T, x naught. This term right here, x naught. So our final position function is going to be x equals vt plus x naught. And you should recognize this as a linear function. It's a line. So we're going to draw some line like this. And if we look at this, if we analyze this function here, what we can see, well, the slope of this line should be v. That makes sense, right? Because if the slope is v at any given point, then we define velocity as the derivative of position with respect to time. So if the slope is v at any given point, then it makes sense that the velocity function is v at any given point. So the slope is going to be v, and this starting point right here, that's going to be this x naught right here, this x sub 0. Because x sub 0 represents our starting point. It's the position we're at time equals 0. And this is not given by v. Just because we know v doesn't mean we know this x0, so this needs to be given in the problem. So here are 3 equations for our constant velocity. Our acceleration is going to be 0 because there's no change in velocity, so there's no acceleration. Our v function is just going to be this v right here. It's a constant value v. So velocity is a constant value. That's why it's called constant velocity. And finally, our position function here is going to be x equals vt plus x naught. It's going to be the constant velocity times the change in time, or the time elapsed, plus x naught, the original x. Our second special case here is going to be constant acceleration. So constant acceleration, again, as the name implies, just means that the acceleration is going to be constant. It does not change over time. So what this means is that our acceleration function here is just going to be some a of t always equals a, for some constant value a. And if we want to graph this on this a over t graph, we're just going to have this straight horizontal line somewhere at a y value of a. So remember, we defined velocity is going to be the integral of acceleration with respect to time, or integral a dt. So we can use a similar method as we did last time. If we drop this vertical here, we can see that if we go to some time t, well, from time 0 to t, the area under this acceleration curve here, or the acceleration function, is just going to be area equals at. So similarly to what we did last time with position and velocity, what we can say now is, well, then v then has to equal at plus v naught, because we still have to add this v naught term to represent where this velocity starts. So if you want to graph this, we again get this linear graph. This slope here is going to be a, as we can see here. This is slope a. The y-intercept here is going to be v naught. So pretty good. But now how do we find this x here? This position function. Well, let's see what happens if we drop this vertical line again. Well, if we drop this vertical line, we see, well, we get a trapezoid, which we can then split into two shapes, which are going to be this triangle over here and this rectangle over here. And again, we're going to assume that some time t has passed. So, well, we can just find the area now of this triangle and this rectangle. So the area of this rectangle here is going to be a equals v naught times t, right? Because v naught is the altitude and t is the base length. So for the triangle, area is going to be half of the base times the altitude. The base is still going to be t, so what's the altitude? Well, we see if the slope is a and slope is rise over run, that means that this height here, this altitude, over t needs to equal a. So that means that this height right here is just going to be at. This altitude is going to be an at. So then this area here is going to be 1/2 at times t, or 1/2 at squared. So this combined area now we can write as area equals 1/2 at squared plus v0t. So we're adding up the area of this triangle and this rectangle right here. So now remember, position is going to be the integral of velocity dt, as we said before. So what does this mean? Well, then we can just let our position function equal this area function first of all. So x is going to equal 1/2 at squared plus v naught t. And remember, we still need to add this final term, plus x naught. Well, what is this? This function here, this is now called quadratic function. So it's going to be a parabolic curve, basically. So we're going to start at some x naught over here. And the position function is actually going to look like this. Parabolic. So it's going to go in some direction or downward. And the velocity, or rather the magnitude of the velocity, is actually going to increase usually. You can also have something, say, going like this or something. Maybe that way down. Maybe it's in the positive x direction, but its acceleration is in, or the negative x direction, so it slows down and then becomes negative. But the idea is, whatever the curve is, it's going to be some sort of a parabolic curve. The only thing we can easily find out from here is that this y-intercept here is going to be x naught. There's not much else you can easily find out about this curve using this formula without some more complicated analysis, but here are these three important equations, basically, that we have for constant acceleration. So we have the acceleration is some constant value a. Velocity, we're going to say, is at plus v naught. And finally, our position function looks kind of complicated, but it's going to be x equals 1/2 at squared plus v naught t plus x naught. So we're also going to box that. So these three equations here are the important equations of constant acceleration. So there's one more important equation I want to derive for a constant acceleration that can be quite useful, and it's something like this. So what we do is first we say, let's give a name to this final velocity over here, whatever the velocity is at the end of this time. Since this is v sub 0, let's call this v1, say. Right, a v with a v sub 1 rather. So now what we can do is we can say, well, the acceleration is just the slope here, right? So we can say that the acceleration equals v sub 1 minus v sub 0 over time t that's elapsed, right? So we can rearrange this equation to form t equals v1 minus v0 over a. And now what we can do with this t solves t over here, which I'm going to box. What we can do with this t is we substitute this t into the equations for position here. I'm not going to go too specific into the math here. It's not hard. It's just some algebra and some computations. But the idea is if we do this substitution, we substitute this quantity of t into this x equation, we end up with this interesting equation, which is that v1 squared equals v0 squared plus 2ax. And this equation here is what we're going to call the no time equation, because we see there is no t in this equation at all. We don't need time to do anything in this equation. So say we have some of these values. Say we have the final velocity, and we have the initial velocity, and we know the acceleration, and we want to find out, well, how much distance has passed with this acceleration going from v0 all the way to v1. Well, then we can use this equation here, the no time equation, if we're not given the time that has elapsed in that time. So this is another equation that can be useful. So in general, these four equations here, I'm going to number them actually. So this 1, 2, and 3, these equations are the explicit equations for the acceleration, velocity, and position of constant acceleration, and they're going to usually go together. And then this fourth equation here, this no time equation, can also be useful in certain problems. So what we're going to do next time is we're going to look at some problems involving constant acceleration, and we're going to use these equations to solve for certain values.